In this second video, we'll begin with a datasheet of the device I selected for my Handy Supply product. The choice of the ADP 2302-2303 device was made based on many factors, including the input voltage range, the output voltage range, the output current spec, external components needed, completeness of the datasheet and design examples, and, most importantly, its price and availability. As I mentioned in the first video, I very much treated this as a learning experience, but from its very beginning I intended this to be the base of a new product now known as Handy Supply. There isn't any use of selecting a device that's either too expensive to use or can't be obtained through standard distribution in large quantities. The latter point was very important should it be that my new product really take off. I learned that it is surprisingly easy to find devices with really wonderful specs, but that can't be found in distribution. Here's the datasheet for the ADP 2302-2303. Even though my purpose here is to hit only the highlights, I want to emphasize that you must take the time thoroughly to digest the datasheet. Read it again and again until you have developed a confidence factor that even if there are some details you don't quite understand about how or why they work the way they do, you nevertheless have developed some comfort level with the device. Spend some time looking at the graphs to get a feel for the operation of the device. From Figure 1, it is very evident that this device doesn't need very much around it to make it work. This was particularly attractive for Handy Supply since it has to be small and inexpensive. I didn't need the enable signal here, so it is tied high. It can safely be tied to VN as shown on page 4 of the datasheet. And this is a good time to point out an example of one of those details that you must not assume. While it was almost certain that Analog planned to allow the pin to be tied to the raw DC input, the general rule must always be, make no assumptions. By design, my Handy Supply boards have LEDs on the output and so serve as the visual indication that the converter is working. Therefore, I didn't need the power good output, which is open drain. But just to be conservative about it, I pulled it up with a 10K resistor to the output. The device is able to regulate between 5 volts and 800 millivolts, as we see here on the first page of the datasheet. There are two methods available to set the output voltage. The first is that Analog makes the device available with built-in output voltages, as we see here on page 26. This effectively eliminates the need for the resistor divider I'll talk about soon. Note that the 2302 is the 2 amp device and the 2303 is the 3 amp device. They are otherwise identical. The pre-programmed output voltages are 2.5, 3.3, and 5.0 volts. The second method of setting output voltage is by means of a resistor divider network shown on the first page of the datasheet. The resistors are set to ensure that when the desired output voltage is reached, the center node of the resistor divider is 800 millivolts, which is then connected to the feedback input. If we go to page 16, table 6, you'll see some pre-calculated resistor values. If you do the math, you'll validate that the divider point is at 800 millivolts for the specified output voltage Vout. The formula for this is here, just above table 6. This is just plain old ordinary Ohm's law at work. Everything to the right of the 0.800 is the ratio. The 0.800 is the internal reference voltage around which the regulation takes place. The remainder of page 16 and the first half of page 17 provides information on the design process that I don't really need to go through here. But as I mentioned earlier, you should spend whatever time with the datasheet you need in order to become comfortable with these details. What I cover next, though, is the calculation for the inductor. The inductor is fundamental to all switch mode designs. It is the transient energy store. What you'll learn, if you spend time with the datasheets, is that the voltage regulation is really a tight oscillation about a voltage reference. The magnetic field through the inductor is either building or collapsing, and the magnitude of that activity is termed and measured as ripple current, delta I ripple in this formula here. It is calculated as a percentage of the output current. As you see in this last paragraph, very commonly the ripple current is designed around a value of 30% of the rated output current, regardless of the device or manufacturer. Occasionally, you'll see published design values as high as 40% and sometimes at 35%, but usually it is 30%. If we ignore the last term, the one with a large parentheses around the numerator and denominator, here, and combine terms, we can treat the formula as a simple ratio between ripple current and inductance. And if that is the case, by the rules of simple algebra, we can therefore interchange L in the denominator here with a delta I ripple on the left side of the equals. And this is exactly what has been done on page 18. The purpose of this transposition is to solve the equation for L, the needed inductor. You'll notice the delta I ripple here has been replaced by the constant 0.3 here, 30%. The formula now also clearly shows us that the inductance depends on the input voltage, the output voltage, the max output current, and the forward voltage drop of the catch diode, V sub D. In the case of the Schottky diode I used in Handy Supply, its spec is 490 millivolts. So essentially, it's just another constant in the formula as V sub D. The only other value in the formula, F sub SW, is the switching frequency, nominally 700 kHz. So, like the ripple current and the catch diode voltage drop, it acts like another constant. What we're left with is the input voltage, the output voltage, and the max output current. It's now a matter of simple algebra. You can create a spreadsheet in a very short time to make the calculation for you to try out various combinations. I'll show you mine in a moment. In general, you must ensure that the DC resistance, DCR, of the inductor is as low as possible for the intended output current. And you must ensure that you derate the device according to the anticipated temperature rise. We'll look more at this in the third video when we use Worth Electronics' Red Expert online tool to help select and validate the inductor. If you watched my intro video on Handy Supply, you should now understand why I made the comment that the inductor is the critical component correlated to the nominal output voltage. The remainder of page 18 discusses the catch diode to ensure that you spec an adequate device. It's pretty straightforward. The Handy Supplies, even with a 3 amp load, do not require a very large diode and can run easily, continuously, at full load without danger of overheating. Page 19 discusses the input and output caps. Again, you'll learn that the general rules are to select capacitors with the lowest possible ESR and with adequate ripple current specs. Most of the time, these will be multi-layer ceramic caps, MLCC. A good rule of thumb is to determine the total capacitance needed, then split it by paralleling caps, which also effectively reduces the per cap ESR. The input caps must have a high enough voltage rating to accommodate the input voltage. In the case of Handy Supply, I want the supplies to support the 20-volt DC spec of the 2302, 2303 ICs, so I need at least a 25-volt input cap. Regarding the output caps, by design, the supply can never produce more than 5 volts DC, so even a 6.3-volt cap would work. However, as a side note, once you've determined the total needed output capacitance, check the pricing and availability for the 6.3 volt, 10 volt, 16 volt, and so on, because it very well may be that the higher voltage caps are actually less expensive and more available. It's just another one of life's little mysteries. Okay, back to the data sheet. For specific cap values, my recommendation here is to simply follow the design examples and, in general, round the values up slightly if needed to guarantee that you've met the output capacitance requirements. Other than the fact that you clearly don't want to buy more filtering than you need, and thereby potentially price yourself out of the market, your PCB layout should accommodate the largest number of caps you're likely to use. You can always not populate one or more of them if not needed. Also, beyond this simple issue of cost, one other consideration is that having too much output capacitance can slow the transient response time. This shows up here on page 19 as delta V ripple. Like many other things, good engineering is often a compromise between essentially exclusive requirements. In the last video, we'll look at the process for selecting and validating the inductor.